All right, let's do an example with our pumping problems. Here's all the info we did before, jumping down to the problem we're going to mess with. So we want to find the work required to pump all the water from the following figure. We assume water has a density of 1,000 kilograms per cubic meter. All right, now there's a lot going on here. And I wrote 1000 G. I'm going to take that crap out. We're going to go straight to it. Gravity times our density will be 9,800. So now it makes it a little bit simpler for us to see where we have to find the area of any slice. So maybe I just take a slice and go right here. We're going to cut this out right here. We're going to cut that slice out. We're going to need to find the area of the slice. And that represents the thickness for the volume, but we don't need to stress about that. And then we're going to need to figure out what the distance traveled is going to be. And the distance isn't going to be so bad. It's just like the lifting problems. It's like the lifting problem. So when we have this, we're like, well, bro, we got to move all this water 10 meters, right? It's got to get up to 10 meters. So we're going to know that our distance is going to have to be 10 minus the y value because, I mean, shoot, if we were down at 2 meters and we got to go up to 10, if that's y, well, what's left is 10 minus 2 or 8 or 10 minus y. That would be the remaining piece there. Okay, so that's going to be our distance. But now here comes the trick. This is where it gets rough. Is we need to figure out the area. How are we going to find the area? What value is this right here? Isn't that x? From the center over to there, wouldn't that be x? I think it would be. Shoot, you know what? We should do something. Oh man, we should do something. You know that we can put this on any sort of axis we want. We can choose where we want our axis. Sorry, struggling with technology. We can put it wherever we want to. We can make this, where do we want to put the bottom? Like, I would think I'd want to put this at, you know, some x comma y, put it there. So if we can take our, all right, I'm going to try and draw this. This is going to go bad. I already know it is. Okay, I'm not too upset with myself yet. And we got this water. Okay, so we got some water in there. And I want to start labeling some points. I like this down here. That's 0, 0. And then if we're looking at just the one slice, let me put it in black. That length there is x. So we're like, oh, cool. Isn't that just, aren't these just circles we're popping out with a radius of x? It kind of looks like a dead drawing that's not happy. So to find the area, that would be pi x squared, right? Well, shoot, I think we have everything. Let's just put it in and see if we can solve. We say the work is equal to 9,800 times the integral of, we'll talk about that in a second. The area is, well, pi x squared times the distance, which we found to be 10 minus y. Do you see the problem? Do you see the problem? It's x, and we're doing dy. We have to convert that x into y's. And here's the game. Since we put this on the xy axis, I want to know, what's that point right there? How far up are we going from the figure? It's 10, right? So our y value is 10. Then how far? Oh, and the x value, that's 4 meters away. The radius of the top of the cone is 4, so we're at 4, 10. Now, this isn't going to be the similar triangles game that you may have seen in a Calc 1 class. It's going to be a little bit different. We're actually going to talk about the slope of the line. This line right here, because we created it in such a nice place. we want to talk about what's the slope of that line. You know, the y2 minus y1 over x2 minus x1. But we already have our y2 or y1. We have an x2 and an x1. And I hope you can see the trick right through this. Because as a student, I just look at this and be like, bruh, x is equal to 2/5 y. So watch for the pattern. So you don't have to go through and build this every time. So as we put it in, we're like, all right, well, what's that slope? Well, that slope is going to be, I don't know, let's call that x2, this one, y2, this one, x1, that one, y1. So we're going to have 10 minus nothing over 4 minus nothing, which is 5/2. That's the slope of the line. And you're like, okay, cool story. I don't care. Well, we have this formula for a line which tells us that y minus y1 is equal to the slope times x minus x1. That's called the point slope form. So why don't we go plug in two values of x and y that we know that are on this curve, and maybe we can figure a little something out. You know, because we already know that the slope is 5/2, so we don't have to do anything there. And this is just y minus, and this is just x minus. So which one do you want to choose? Do you want to use 4 and 10, or do you want to use 0 and 0? Yeah, me too. Let's use 0 and 0. So what we find out is, y is equal to 5/2 x. And what we're trying to do is we're trying to solve for that x in terms of y. So we're going to multiply that over to the other side, and we're going to find out x is equal to 2/5 y. Can you see the pattern? Can you see how you could jump past this? You don't want to reinvent the wheel every time. What's 4 divided by 10? Isn't that 2/5? Isn't it just the slope flipped over? Isn't that just the slope flipped over then multiplied by y? I think it is. So now our work is 9,800. The integral of, I'm still not talking about that yet, times 10 minus y dy. And now we can pop in our 2/5 y. All right. Now we have to talk about the bounds. I've been avoiding the bounds. I've been staying away from the bounds. Now the bounds, that is talking about how much of the water we are going to move. Because you notice it's not full. There's still 2 meters left. So our bounds of integration, just like we did when we revolved around curves, is only the shaded region. Now, the distance it has to travel varies. That's a different thing. It has to move 10 meters total. But we look in here and we see it's only 2 meters to the top. So really, we're starting down at y equals 0, and we're only going up to y equals 8. So the bounds of integration only have to do with the shaded region, or the region of the liquid. So now we have our bounds. This is a lot, huh? Now you're going to be required to come up with this on your own. Now, I'm just going to tell you, on an exam, there's your answer. There's only so much time I have with you when we take a test. 2 hours, 5 minutes to do all these gosh darn problems, what? Revolving about curves and finding area between curves and finding finding lengths of curves and finding surface area. Dude, a lot of these problems will probably just be a setup. So that would be sufficient on a test if I just said set it up. But I'm going to try and solve this thing. Like your homework's going to ask you for probably some rounded decimals or something. So I'm going to get that constant out of there. That was a pi. We're going from 0 to 8. Let's square all that stuff. 4 over 25 y squared times 10 minus y dy. And again, I'm really freaking lazy. I'm too lazy for this nonsense. I don't want my 4 over 25 in there. I don't want to have to go through and do all that work. Why don't we just do this? Times 4 over 25. Now what is 9,800 divided by 25? I know it goes in evenly. Well, that's 392, and 392 times 4 is going to be 1568 pi, the integral from 0 to 8 of y squared times 10 minus y dy. Again, I wouldn't expect you to be able to do this with a calculator, or without a calculator. Those numbers are too big. I don't like big numbers. Not on tests. But at home, when doing homework, all day long, let's go. And now we have this integral to solve. But it's all about getting them constants out. 1568 pi times, oops, I gotta do the whole integral. 0 to 8, so we get 10y squared minus y cubed dy. And these numbers are going to get quite large. But again, since this is not like a good test problem as far as solving in this manner, you will need to do stuff like this in your homework. These numbers are large. I don't know 8 to the 4th. Shit, I don't know 8 cubed. But my calculator sure as hell does. Hopefully this is really showing you that your teacher is not going to make you do crazy amounts of multiplication by hand. So let's run it through. Let's see what we get. We get 1568 pi times 8 cubes. I think I lied. I think it's 512. Is it 512? Yes. So then 512 times 10. And then we see if it's divided by 3. Does it work? No. Times 3. Put it right back. So we get 5,120 over 3 minus 8 to the 4th divided by 4. That's going to be a whole number, I believe. Oof, divided by 4. And we get 1024 minus absolutely freaking nothing. Well, now I'm going to multiply both those by 3 and figure out what we get, top and bottom. So we get 5,120 over 3 minus times 3. 3072. And notice I'm not doing a bunch of rounding yet or anything, and just running the problem. We round at the end. And that's 2048, not divisible by 3. And 1568 is not divisible by 3, so now we're just going to multiply this by 1568. Oh my goodness. We got 3, 2, 1, 1, 2, 6. Come on, man. Come on, man. We got this. We got this. Pi over 3. Now, if you want to put that into a calculator and run your answer, and you're like, oh my goodness, that took a lot of freaking work. 3362827.797 joules. So what is that? So I'm purposely not speaking it as I'm doing it, because I need to look and be like, oh, it's 3,362,800 and... Is that a 2 or a 7? 2! 27.77 or 797 joules. Now, if we were doing this on a test and I was a total butthole about giving you everything, this would be your answer by writing joules at the end, but these numbers are way too big. Once again, I think that this would be sufficient right here on an exam before plugging it in. Because shoot, I think the hard work is setting it up. I don't think the hard work is actually putting in the numbers and hitting stuff with a calculator. So please be ready to set up a pumping problem. This does have a probability of being on your midterm. I don't know, I'd probably say it has a 1 in 3 chance of you having a pumping problem on your midterm, and I'm guessing the lifting the chain, you have about a 90% chance of having that. And then we have one other topic, which is called hydrostatic pressure, and that's what we're going to move into next. Hope to see you there.